So for the title of my talk, I chose a quote by Richard Feynman. Nature isn't classical, damn it. So if you want to simulate nature, you better make it quantum mechanical. In the following, I would like to convince you that he was right. Oops. So first of all, I'm going to start with explaining to you what exactly is a simulator. I'm going to go on to tell you how are such quantum simulators useful, in what areas of science they're applicable. I'm going to continue to talk a little bit about how to make a quantum simulator and how do they physically look like. And I'm going to finish off with mentioning my own contribution to the field. So what is a simulator? I'm going to start off with a bit more tangible analogy than the world of quantum mechanics. So imagine you want to build a plane. One thing you might want to do is to use your knowledge of airflow and of kinematics to design a numerical algorithm. Then with this numerical algorithm, you can simulate on a computer what would happen to the plane, to its wings, to its body, when it flies in the sky. Okay, but such a computer simulation has certain approximations because it includes only those phenomena which we ourselves put into the algorithm. So if you want to make it a little bit more precise, we can actually put our plane in a wind tunnel. This physical simulation exactly mimics the situation of a plane flying in the sky and hopefully also give us information, some insights into the things that we simply did not consider in our numerical models. So in my talk, I would like to talk to you about the quantum equivalence of this sort of physical simulators. So what for do we need quantum simulators? One of the main areas where scientists see their applicability are simulations of materials. So materials, novel materials, drive progress in plenty of areas of science, from medical physics to aerospace. So we'd like to understand them better. We would like to develop more and more properties of those. So one of the examples that we would like to look into are, for example, high-temperature superconductors. So nowadays, they go up to something like minus 70 degrees Celsius. And although we discovered them more than 30 years ago, although we took them apart, we know what's inside, we still have a problem that we are not quite sure how those components work together. So what we would hope that a quantum simulator would not only help us understand what gives the high-temperature superconductors their properties, but also with this knowledge, maybe bring the temperatures where they're operating to higher levels. Another area where quantum simulations can be useful are simulations of biological molecules. In recent years, we get to know that more and more biological processes actually include quantum mechanical effects. For example, certain enzyme-mediated chemical processes actually use a phenomenon of quantum tunneling. The problem is that biological systems are messy, so it's very hard to study what is happening in this setup, whereas in a clean setup of a quantum simulator, we have a better, more direct insight to study those phenomena. Okay, but why don't we just mimic the quantum mechanical laws on our normal classical computer? Oops. So let's think about it. Quantum mechanics is a probabilistic theory, meaning that a system has only certain probability to be in different configurations at any given time. So if you want to make a normal classical computer simulation of a quantum mechanical system, at every given time, we have to keep track of all the configurations that the system is in with all the corresponding probabilities. This makes us have to actually keep track of an exponential in system size number of variables. So let's imagine we want to simulate a system of n electrons. Then we have to keep track of 2 to the n variables. If you choose this n to be a small number of 40, then we already need a computer like that. So this is a state-of-the-art supercomputer currently in Los Alamos National Laboratory in US, and has an operating power of 10 to the 15 floating point operations per second. This is how much computational power we need to simulate exactly merely 40 electrons. If you want to go a little bit higher, for example, let's say 300 electrons, then we already need as many variables and the estimated number of electrons in the universe. So I hope you agree with me that it's pretty a lot and it's not very feasible to simulate exactly quantum mechanical systems on a classical computer. So how would we go about making actually such a quantum simulator? So what we have in nature, let's say roughly what we have in a material, are atoms in fixed positions, and they form some sort of scaffolding and there are free electrons which move about in the scaffolding. And the interaction between the electrons and the electrons with the atoms, they govern the properties of the material. And so this would be our equivalent of the plane flying in the sky in my plane analogy. Then if we want to build our equivalent of a wind tunnel, what experimental physicists do is to form this sort of scaffolding from laser light, and then the role of electrons is played by ultra-cold atoms. So we take atoms of cesium, rubidium, or lithium, and we cool them down all the way to nanokelvin range, where they are truly quantum objects, and we have really high level of precision in manipulating them. And simply with changing the frequency and intensity of the laser light and applying magnetic field, we can engineer what sort of interaction is happening between the atoms and how do they move about in this lattice formed by lasers. This is much easier to manipulate than in the actual material, where to change the properties of it, we have to prepare a completely new sample. And also, in the actual material, we don't see directly what is happening there. We rely on some measurements to infer what is happening with the electrons themselves. Whereas in a quantum simulator, we can really observe the positions of the atoms. We can really observe where do they move. So we have a really direct way of observing them. So now I'd like to show you how such a quantum simulator looks in a laboratory. So this is something like this. It's a complicated setup with plenty of optical and electronic components, but once it's put together, it gives us such a high level of precision that we can handle up to a single atom. And now I'd like to show you a photograph taken here at Oxford, where you see really a single atom isolated, where I personally find really impressive. So now I would like to move on to talk about my own work in open quantum systems. So what are they? Open quantum systems are systems which interact with their environment. And really often, quantum simulators are such open quantum systems because we require them to interact with the environment of the laboratory they're in. So the only problem is that now we would like to develop a mathematical description of such a quantum simulator which reacts with the laboratory environment. So if you think back to the analogy of a plane, the success of this physical simulation in a wind tunnel relies on the fact that we know something about the physics of airflow to interpret the outcomes of a simulation. So now I would like to develop a similar framework for this case. So the first efforts to do it date back to late 1970s, when the Lindblad equation was formulated. The only problem is that it's a differential nonlinear equation. And for any experts in the audience, is a non-unitary time evolution equation, meaning it's super difficult to solve it. Analytically, up until now, we have solutions to only the simplest non-interacting models, and numerically, we did not get much further. So my work is to reformulate this equation to the form that actually we possibly are able to obtain a full analytic set of solutions to this sort of an equation. And just to give you a taster of what sort of equations we are talking about, this is one of them. It looks long, big, and scary, but from this one, we are actually able to extract some physically meaningful information. So now let me tell you how we go about with comparing this scary equation to the experiment. So in a typical quantum simulator, this is what we might see. So those are snapshots of the positions of the atoms. So every dot corresponds to the position of the atom, and there are snapshots taken at different times. So looking at those pictures, we can calculate correlations, meaning interdependencies between positions of individual atoms in space and time. The same sort of correlation functions we can extract from the equation I just showed you a second ago. And then, by comparing the two, we can actually find out whether the mathematical theory we're developing is valid. So people have done a similar thing for a bit simpler systems, closed quantum systems, meaning the ones which do not interact with the environment. And as you see, so here there are those correlation functions computed either from a mathematical equation below or from those pictures of the atomic positions above. And we can see that time by time, physicists manage to prove the validity of the theory by comparing that these two are matching. So I'm trying to do a similar thing for those more complicated open quantum systems. So here, there are some of my predictions of how those correlation functions should behave for this particular open quantum system, which is one of the candidates for high temperature superconductivity modeling. And experiments for this have not been done yet, but I hope they will soon follow, and I hope I'll be able to validate my theory. Thank you for your attention.